We know how to calculate the band structure with the DFT method. Next, I will talk about how to understand the band structure. In the topology, there's a very simple but very important concept is the band inversion. Actually, when this is the typical band structure, the band theory maybe is one of the most successful example to apply quantum mechanics in solid material. But the band theory classifies materials into metals, insulator, semiconductor, and semi-metal, for example. And it also tells us when we apply electric field, the electron will move in the band structure. And with this theory, we understand why an insulator or semiconductor does not conduct, why a metal and semi-metal conducts. Overall, most of the time, actually, especially in the metal case, we think about a one-band case, only one band structure. Even in the semiconductor, sometimes we only talk about on the top of the valence band or on the bottom of the conduction band. Anyway, it's a one-band model picture. The idea of topology is simply, let's go beyond this one-band model. Let's go to two bands. If we start from an ordinary insulator, insulator means we have a conduction band and a valence band. They are separated by an energy gap. Usually, these two bands have different symmetry. For example, here, the valence band is composed by the p orbital, the conduction band composed by the s orbital. And now let's do some thinking experiment. Suppose we push these two bands close to each other. When they're close enough, the band will cross. After the crossing, they will hybridize. Then when they open a gap again, we have a new insulator. This insulator, same as the other insulator, it has a band gap, has valence band and conduction band. However, the difference is, let's look at the gamma point, the center. The wave function now mixed, like the valence band. It evolved from the p orbital to the s orbital, then go to the p orbital again. And that is opposite for the conduction band. We can mimic the topology by a strip. For example, here, the normal insulator is a normal strip. And you go on the surface, you only have one orbital. The second insulator, we can mimic it as a Möbius strip. If you go on the surface, you will meet another surface, right? This is a mimic. You go from mix p orbital and s orbital. Yeah, we use this idea of topology to classify these two band structure. Clearly, these two band structure are different by a band inversion. This is the concept of band inversion. They are topologically different. Different in a sense we cannot change one smoothly to another without closing the gap. Closing a gap is treated as a violent change. Today, we call them the first one as normal insulator, the second one with the band inversion is the topological insulator. Then now let's see topological insulator, how special it is. Let's observe the consequence of the band inversion. Let's first do an experiment from the normal insulator. We put another normal insulator as its neighbor. They form an interface. Think about this band structure. The valence band will deform smoothly to the valence band, and the conduction band to the conduction band. In this sense, okay, nothing special will happen, right? However, on the interface between the normal insulator and the topological insulator, because the wave function symmetry change, this conduction band will evolve to another valence band, and the valence band to the conduction band. And for this reason, at the interface, the band gap must close. The band gap close at the interface. It means the interface is metallic, right? Now there's something a little weird, right? We put two insulators together, but in the interface, it becomes metal. Now let's go one step more. Let's think about the vacuum. If we treat vacuum as an insulator, then between the interface of vacuum and normal insulator, okay, it's a smooth change, nothing could happen. But between vacuum and topological insulator, the band needs to invert back. The consequences, the surface, will be metallic. That means if we have a topological insulator, although inside the material is insulating, it does not conduct, but on the surface will be metallic because the surface is the interface between the material and the vacuum. Then we know a topological insulator will have a metallic skin surrounding it. And the metallic skin comes directly from this band inversion in the bulk. Here, we usually call it bulk boundary correspondence. The bulk means bulk is inverted. Boundary has metallic states. If bulk is not inverted, it will not have this state. We know surface state is not a new concept. Even silicon has a metallic surface state. Then what's the difference between a topological surface state and an ordinary surface state? And we know silicon can get oxidized. For example, if it has a surface state, after some oxidation, actually this surface state just disappears. Silicon becomes an insulator inside and outside. But what happens for topological surface states? Suppose we make the surface dirty or we oxidize the surface. Okay, we kill the surface states. Then we create a new insulator on the surface. Between this new insulator and the topological insulator, this new interface, it becomes metallic again. This simply tells us as long as the bulk is inverted, we will have a metallic surface state. The metallic surface state is super robust. Okay, overview this logic. What we learned is if we have a band inversion, the surface will become metallic. And this is exactly the idea of a topological insulator. And in the bulk, if the band is inverted, we will have metallic surface states. Actually, this surface states, the dispersion usually form a Dirac coil. And like shown in this figure. But if the bulk is not insulating, what happens? Actually, sometimes it do happen. If we have a band inversion, but in the end, the bulk has some gapless point. This gapless point, actually, they are three-dimensional Dirac point. And then on the surface, what could happen? There are topological states. Let's go back to this logic. Actually, the topological surfaces comes from the band inversion. We don't really care the bulk is fully gapped or not. And therefore, because this metal also has a band inversion, it will have topological surface states. But different from this Dirac coil, this surface states usually has a very special feature. We call it Fermi Arc. It's a Fermi surface. It's not a closed loop or a circle. Actually, it's an arc, just a part of the line. And here, this general picture is we have two bands getting inverted. We will have topological states. But if we have more bands, for example, if we have 4 bands, what will happen? If we have 4 bands, 2 by 2, they are both inverted. Then, follow this logic, we will have 2 surface states. We have 2 Dirac coils. But since these 2 Dirac coils appear in real space in the same position, also in energy, they will hybridize. They will have interaction to each other. And then there's a question, will they totally kill each other or there's something left? In quantum mechanics, we know if we have some additional symmetry, actually the symmetry will protect these states. For example, if we have a mirror symmetry, in the mirror plane, the crossing point of these 2 Dirac coils will remain gapless. Then the consequence is the surface is still a metal surface. And go to higher order, actually there's a higher order topological insulator, means actually not the surface. Even the surface, there's no symmetry protection, but on the hinge, on the boundary of 2 surfaces, and it can still remain metallic if we have additional symmetry to protect it. Then overall, this idea is if we have a 1 band inversion, we will have a single Dirac coil on the surface. If we have a more band inversion, we ask, are there additional symmetry to protect the surface states? If there are, it is still a topological state. And they are called topological crystalline insulator. Crystalline means we need some crystalline symmetry to protect it, or higher order topological insulator. Higher order means the special boundary states is not a surface, but a hinge, one-dimensional hinge. Now we already learned this simple band inversion scenario and how it creates these topological surface states. But how to really quantitatively characterize a band inversion. And next we will talk about this accurate criteria like parity to decide the exact topology.